Let us find out potential energy in an external field. Here we have given an electric field, that is E, in the space. We know nothing much about the source of the electric field, and we don't need to really bother about that also. So we don't know what is the source of this electric field. All we know is that the electric field is E, and in this region the electric field is E, and the potential at a point, let's say this point, is V. Okay, and we need to find out the potential energy of a charge Q which is brought from the infinity to this point. So let's say from infinity this charge Q is brought, okay, when the external electric field is E, and subsequently it results into potential V at this point. Okay, so we have learned in the previous section that to find the potential energy, that is U, we actually multiply the charge on which the work is being done to the potential, right? And that is it. This is a scalar quantity because it is the potential energy. Energy is a scalar quantity, but still we need to use one vector just to say that there is a point P we are talking about whose position vector is R with respect to some origin. So this is the origin, okay, and from the origin the point P is R distance away in a particular direction, that is the R vector, and the work is done on the charge Q to bring it from infinity to this point P, okay, when the electric field is E or the potential is V, okay, at that point. And why we have to use this position vector R? Because potential will change at every point, because potential is actually proportional to 1 upon R, 1 upon the distance. So at every distance the potential will change. So that's why potential at a particular point has a particular value. So we are considering that value of the potential. That's why we are, okay, and this is our potential energy in an external field. So according to the NCERT book, what it says that potential energy of Q at R, vector R, in an external field is Q into V at R, where V at R is the external potential at the point vector R. This is all the build-up of the concept what we have already covered. So if you find any confusion, if you really don't understand certain thing, you can always go back to the previous section, the previous video, and then it will be all right for you. Okay, okay, let's move ahead. So if an electron with charge Q, that is E is equal to, on electron the charge is 1.6 into 10 to the power minus 19 coulomb, is accelerated by a potential difference of delta V, that is 1 volt, it would gain energy of how much? The energy is Q delta V or QV we are talking about. So already here the external potential is given 1 volt, okay. So the energy, potential energy would be Q delta V, and that is equal to 1.6 into 10 to the power minus 19 joule. And this unit of energy is defined as 1 electron volt or 1 eV. So 1 electron volt is actually 1.6 into 10 to the power minus 19 coulomb. The units based on EV are most commonly used in atomic, nuclear and particle physics. and 1 kilo electron volt is 10 to the power 3 electron volt, okay, and mega electron volt is 10 to the power 6, and giga electron volt is 10 to the power 9 electron volt, and so on, okay. And there's tera electron volt also, that is 10 to the power 12 electron volt. There can be penta also, that is 10 to the power 15 electron volt, and so on, okay. Oh, sorry, it is peta. So 10 to the power 15 is peta. All right. So peta electron volt. Since you know about the single, charge, that is Q1, which is brought in the external electric field, and what happens to the potential energy stored on that charge, okay. Now just include more charges. We are talking about system of charges, so just take 2 charges in the system. Now it is quite easy to understand, like we already talked about, there is external field E, okay, and in that field at particular 2 points, let's say at point 1 the potential is V1, at point 2 potential is V2, and now we're talking about 2 charges. So we bring 2 charges from infinity, one at this point, another at other point. So what will be the potential energy stored in these 2 charges? Total potential energy of this system of charges, okay. So first of all, in an external field, we have just proved that the potential energy is actually Q1 into V1. Suppose this is at R1, and then add it to Q2 into V2 that is at R2, okay. And if you remember in the previous section what we talked about, that we have to bring the charge one by one, okay. If you bring the first charge on that, to bring it from infinity to this point, that's the potential. Then we bring the second charge, then this is the potential. But then the second charge will also feel a potential or a force due to the first charge, okay. This potential energy is developed because of the external field we talked about, E, okay. And here also this is developed because of the external field. But then when we bring Q2 in the picture from infinity to this point, at that time Q1 is already here. So Q1 will also exert some extra force other than the force exerted by this external field E, okay. So that will also get added. And since if you check the previous section, we talked about how to derive the potential energy of these of our charge when we bring it in front of another charge. So that is actually the other charge Q2 and the potential due to the charge Q1, okay. And this is actually Q2 and Q1 upon distance between these 2 charges. So let us say R12, okay, and divided by 4 pi epsilon naught, okay. So our VQ1 is actually Q1 upon 4 pi epsilon naught R12, okay. So this will be added in the overall potential. So your answer will be this: Q1 V at R1, Q2 V at R2. These potentials are different here, remember, because these are at 2 different positions in space. And this is the potential due to external field at R1. This is the potential due to external field at R2 on Q2. And then this is the potential, and this is the potential energy we are talking about, okay. Potential, when I said potential, I only focus on the V. So the potential energy is charge multiplied by potential. then charge multiplied by potential. And this one is what we talked here, that because of the presence of charge Q1, Q2 will face another amount of work done, and that work done will be stored as potential energy, so extra. So, and that is Q1 Q2 upon 4 pi epsilon naught R12. R12 is nothing but the distance between these two charges. Okay. So that is the total work done and also the total potential energy. And finally, let's learn about potential energy of a dipole in an external field. We know about dipole that it is a combination of two charges. One is the negative, one is the positive. And it is separated by distance 2a. And the center of the dipole is at equidistance from both the charges. Okay. The dipole moment is P, which is a vector quantity, and the direction is from negative charge to positive charge, and that is equal to 2aq. And we'll use the unit vector here, P. Now we already know that there is when the dipole is there in an external electric field, there is a torque working on it. The torque is tau is equal to P cross E. So if you want to sense the direction of this torque, it would be so if the electric field is due to the positive charge, so this will push the positive charge away. So in that way we can say that the torque is something like the one I am drawing in the figure. What you can see, this is the direction of the torque. And if there is cross product, we also know that this will give tau is equal to P, magnitude of P and magnitude of E, and then sine theta. And theta is the angle between the dipole moment and the electric field, and what you can see in the figure. And now you have to think about that this dipole is not here from the beginning. So we if we want to find the potential energy of a dipole in an external electric field, then we have to think that we are bringing this dipole from infinity to this point or to this place where you can see it now. So whatever this dipole is experiencing, that torque, the same amount of torque is is applied to bring it here, to bring it in the place. So as you can see that it says that an external torque, tau external, is applied in such a manner that it just neutralizes this torque, the torque what we are talking about, and rotates it in the plane of paper from angle theta naught to angle theta 1 at an infinitesimal angular speed, very small angular speed, so that we don't create any angular acceleration. And the work done by the external torque is what will be stored as the potential energy for the system, for the dipole. So we can say that work done is equal to the external torque multiplied by the small angle delta theta, and the limits are from theta naught to theta 1. Okay, and that is actually equal to already the torque whatever it is working here, so that the value of the external torque should be exactly equal to the torque already the dipole is experiencing inside the electric field, and that is Pe sine theta dt, that we already know. So if we want to fix the limit from of the theta from theta naught to theta 1, then the total work done would be Pe. P is the dipole moment, E is the electric field, and then we will just subtract the cos thetas here. Why? Because if we integrate the sine theta will get cos theta. Simple. Cos theta, so it is cos theta 0 minus cos theta 1. So integration of sine theta d theta is actually minus cos theta. That's why we are using theta naught first and then theta 1 later. So it had to be theta cos theta 1 minus cos theta naught, but because sine theta d theta is minus cos theta, so we have changed the order. And this is the potential energy stored by the dipole in an external field. As we already talked that these theta naught and theta 1, the difference between these is very small. That is the infinitesimal angular speed we're talking about. So, and very small angle we talked about, and we then want to integrate it. Okay, so and after the value of integration, this is what we get. And here we take that initially our theta is actually theta naught is actually pi by 2. We will discuss this later in a better way, but for now just understand this is what happens. And finally we go to the value theta, where we say that potential energy is stored. Okay, and if we do that, then cos pi by 2 is actually 0. Okay, cos pi by 2 is actually 0, and so we actually multiply PE by minus cos theta. That's why our PE cos theta is actually minus P dot E. Okay, we can write it as a dot product because it is PE cos theta. Okay, and minus sign because what we can see it from here, and that is the potential energy of the dipole. We have used the torque method and we arrived at the potential energy as minus P dot E. All right, now here we use the torque method. Tau is equal to P cross E, and this is how we arrived at the potential energy. But there are two charges, and we can solve it in other way also. We can derive the potential energy in other way, thinking that it is a system of charges that we have already discussed. So what is the potential energy of a system of charges of two charges in an external field? So this external field is given E, and then there are two positions where we will bring the charge from infinity to these points, and since this is a dipole, so distance between them is 2a. Okay, and both the charges are of equal magnitude, only the signs are different. So one is negative charge, one is positive charge. So here, so let's take the first charge positive and second charge negative. It's convenient to do what is given in the book here, and it won't actually change the result. You change the charges positions, it won't do anything much. All right, so let us do. Now the potential energy of the positive charge in the presence of electric field E, where the voltage is V and maybe at R1. So that is simply Q charge multiplied by voltage at R1. Potential at R1, not voltage, I would say. And then plus, it has to be plus, but since in dipole one of the charges is positive and one of the negative, so that's why this negative is come, and then it will be multiplied by the same amount of charge and then multiplied by VR2, potential at the position R2. Okay, so this is done. Then we have we saw that for a system of charges, these are the potential energy due to the external field, but at the same time there will be another potential energy on charge Q2 due to the presence of charge Q1. So charge Q1 will also exert some force, and due to that there will be potential, and once the potential is developed there will be potential energy, and that is actually equal to, so in that it has to be added, but again the charges are of opposite signs. That's why we are using negative sign. One is positive, one is negative. So we have to add the potential, but this is the value of real potential, that is multiplying both the charges. So that is q square divided by 4 pi epsilon naught, and the distance between these two charges is given 2a, that is the distance between the charges in a dipole. So that is 2a. Okay. Okay, the next step is really interesting. Now, since we know this is our dipole, there is a dipole moment P and there is electric field E, and the angle between them is theta. Okay, now this is 2a, the length of the dipole. Now, if we have to think in a way that we have to derive the value of these two potentials in an external field, so we can use the relation between potential and electric field, in which we talked about if the potential surfaces are normal to the electric field, then the distance between these two surfaces, that is delta L, okay, this when multiplied by the electric field, so E multiplied by delta L will give the potential, okay, or the potential difference between these two potentials. So here we can apply this rule, and to be honest, from here, from the figure, 2a cos theta is that delta L, the normal distance between the two potentials. Okay, so from these two findings we can write delta V here. The delta V is the change of the potential. So actually Q is common, Q is same in both the terms. So we can write the value of delta V as E multiplied by 2a cos theta. So E 2a cos theta, that is multiplied by the Q, what you can see in the first two terms here, and then minus q square upon 4 pi epsilon naught 2a. Okay, and from here you can see that 2aq is our P, and then E cos theta minus q square 4 pi epsilon naught 2a. Also, we should also talk about the sign here. The negative sign will come in front of PE cos theta. That is because the force which we are equating it to the external force which needs to bring that unit positive charge from infinity to that point. We are talking about this kind of force here. So that force is in opposite direction to the force already exerted by the system. So that brings the negative charge, negative sign. And here the second part is q square upon 4 pi epsilon naught 2a, what you can see here. This part is cancelled out. We just ignored this part. It is because this is a constant value which will be added to the dipole's potential energy if we take the dipole somewhere else. So that's why the constant is insignificant for potential energy, and we can drop the second part. Okay, and we'll only focus on minus PE cos theta. And now you can see that minus PE cos theta is there. And if cos theta is there, so to make it 0, that is our initial position of the dipole, and that theta we are taking to pi by 2, because cos pi by 2 will be 0. So in the beginning, the potential energy should be 0, and when the external field is applied, or the dipole is brought in the external field, there should be some potential development. Okay, and that development is when cos theta will have some other value other than 0. Okay, so that's why we talked about here that our the range of integration, the limits of integration is from pi by 2 to theta. Okay, that's why theta naught is pi by 2. Alright, so this is the final expression for the potential energy due to dipole in an external field. Okay, that is minus PE cos theta, or minus minus vector P dot vector E. Thank you. If you have any confusion, you can always write the comments, and you can also visit www.proteacher.in.